Right, hello and welcome. We're taking a look at section 4.5. All right, so how derivatives um, can kind of help us with the shape of a graph. Okay, so we kind of know certain things about what derivatives do, and that's great, but now we want to be able to use those derivatives to help us create a graph. Now, I will be the first to say that current technology, all right, that is widely available to everybody in the world, has made a little bit of this idea unnecessary. Okay, so I will lead with that. Things like Desmos and graphing calculators in today's world allow us to figure out these things very easily. Okay, uh, but not the point of the idea. We're learning calculus. We're doing some things to really figure out the why of how these functions work and how these graphs look. Why does it look like that? Okay, uh, how does the math back that up? Okay, so not just looking at a Desmos graph, not just looking at your calculator graph, but let's figure out the why behind it. Okay, so with that being said, we know that when a function f is increasing, that means its derivative should be greater than zero. All right, the derivative is the slope of our function. So if the slope is greater than zero, positive, that means the graph is going up on that interval. All right, if the graph is going up, this is still going up. All right, and that derivative would be increasing. Okay, so both of these two shapes, the graph is going up. All right, the graph is increasing. That's good. But these two are two very different shaped graphs. All right, so the shape is going up, but in two very different ways. Okay, here this function is decreasing from left to right. So our first derivative would be 0. All right, here it's also decreasing. So our first derivative is not 0, less than 0. It's negative. All right, and so we have this idea. Okay, but again, notice how this decrease is different of a shape than this decrease. So a derivative, first derivative, can only tell you so much about that shape on that interval. Okay, and then we kind of learned some other ideas in the last couple sections. We learned about when the derivative is equal to 0 or when it's undefined, how that tells us important things. So when it's equal to 0, all right, like here we get extrema, so absolute minimum or relative minimum. Here we get, a derivative equal to 0, so relative or absolute maximum. This spot was a saddle point. Yeah, the derivative was 0, but it kept increasing. All right, so that was something we talked about. Here, our derivative is undefined. That's like a sharp turn, okay, or potentially a vertical slope. It looks like it's kind of reaching a vertical slope right here, but that derivative is undefined there. And then in between these important points, we can kind of figure out, hey, the derivative here is positive, and our function's increasing. The derivative between these two is negative, and our function is decreasing. The derivative here is positive. That's why this was a saddle point. All right, so our function was increasing and increasing, and here our derivative is negative. All right, and so we are decreasing. We talked a little bit about how you can do this on a sign chart. I'm a big fan of sign charts. All right, so we got our A, our B, our C, our D, our critical points. All right, so undefined here, 0, 0, 0, and we can talk about how our f prime in that zone was positive, negative, positive, positive, negative. So we talked about how we can make a sign chart out of these things. All right, so what we want to be able to do is in thought be able to do these things without having to rely on a graph. All right, the graph can be backup for us, not have to be the true, the way we look at this. So if we just have an equation, we should be able to find extreme values. We should be able to determine intervals of increasing and decreasing. We should be able to do this. All right, so to figure these out, we find our derivative. 3x squared, 2 times 3, negative 6x, minus 9, and the 1 goes away. All right, derivative of just a constant is there. That is a quadratic, so we want to set it equal to 0 and solve. I see a common factor of 3. And I think this can even factor. Does something multiply together to give us -3? That adds together to give us -2. So our two critical values are x equals +3 and x equals -1. All right, so these are the two spots that we might have an extreme value. Okay, but we also then want to find our intervals of increasing and decreasing based on this. So I know my slopes here are zeros. Okay, but what about if we put a number in between these two things? Okay, so is the slope positive, negative, or I know it's not 0, in between these two. So let's pick a number in between these, -1 and 3. A good number to choose would be like 0. All right, so since I know it's 0 at these two spots, everything in the middle is going to have the same sign. It's either going to be positive or negative, increasing or decreasing. Okay, so I just need to test one point. Don't have to look at all of them. Don't have to test all of them. Just one in the set. So a number in between -1 and 3 is 0. I can plug that into my equation, either here, here, or here. It's probably easiest to plug 0 into this. 0 squared, 0 times 6. So we get -9. So our function in this zone is decreasing. Our derivative is negative. All right, a number bigger than 3, like 4, would probably be easiest to plug in right here. 3 times 4 minus 3 is 1. 4 plus 1 is 5. So 3 times 1 times 5 is a positive number. All right, and then choose a number over here. All right, so our slope, our derivative was positive, so our function is increasing past 3. All right, so pick a number smaller than -1, like -2. -2 minus 3 is -5. -2 plus 1 is -1. So 3 times a negative is a negative. So we are a positive. Negative times negative is a positive. So we are increasing. All right, so overall, we can say that we are increasing on the interval from -infinity to -1, and then from 3 to 4, not 3 to 4, 3 to infinity. Notice we are using the open parentheses here, the open intervals, because at -1 and at 3, we have a slope of 0. That is not increasing or decreasing. All right, that's a 0. We are decreasing from -1 to 3, and that's just that one interval. And then these two things, since it does change from increasing to decreasing, so it's going up and then going down. So that means this spot would be a relative, I don't know about absolute, probably not absolute, but a relative maximum at -1. And since we went from decreasing to increasing, that means the 3 would be a relative minimum. Now, if I want to find out the matching y coordinates for those 2 points, I'd have to take these two numbers and plug them into the original equation, not into the derivative, but into the original to find their matching y values. Okay. All right, so let's do another one. Actually, let's check it. All right, as we're learning stuff, it is kind of nice to be able to check things. So we got x cubed, 3x squared, 9x minus 1. All right, so taking a look here, do we have an increasing function until we get to -1? Yes, we do. Do we decrease from -1 to 3? Yes, we do. Do we increase from 3 on? Absolutely. All right, and we do have those absolute, not absolute, relative minimums and relative maximums. The matching y values are here. That's great. But we knew these x values, we could have found those. Did we care in this problem at all about that point, that point, that point, or that point? No, not at all. Okay, so we were just looking at the shape of our graph. How is it increasing, decreasing? When do we have these critical maximums, minimums, or saddle points? All right, we're not looking at roots. We weren't looking at y-intercepts. Okay, we were looking at the shape of our graph. All right, so next up, let's try this one. We've got some 1/3 powers in here. That's kind of fun. All right, so our derivative, 1/3 times 15 is 5. Then we have to subtract 1 from 1/3. That's negative 2/3. 5/3 times 3 would be negative 5. The 3 times 3 would cancel out. X to the take away 1 from 5/3. So 5/3 minus 3/3 would be 2/3. All right, so a fun quote unquote derivative. All right, let's see. So we want to solve this thing. We want to set it equal to 0. Now, I hate negative exponents, so I might put this at the bottom and make it positive. All right, so over here, we want to solve this thing. So I might take this negative number, this negative value, move it to the other side. All right. Actually, before I do that, is there anything that would make our slope, yeah, we're talking about zeros, but right now, is there anything that would make our slope undefined? A number that would make us potentially divide by 0? Yes, there is. So I know x equals 0, we have an undefined slope. All right, so it probably gets vertical when x is equal to 0. All right, so that's good. We have to know. Again, it's because of this spot right here. Okay. All right, but now we're still solving for any, when it does equal 0, not undefined. So what I can do here is maybe cross multiply. So 5x to the 2/3 times x to the 2/3, we would add those two exponents. That would be 4/3. Divide by 5. All right, so to solve this thing, to get rid of this 4/3 power, we can kind of like move it to the other side. We can raise each thing to the 3/4 power. The 4/3 times the 3/4, you do power times a power, you multiply, would be 1. And then 1 to the 3/4 is still 1. Right. Cool. Actually, let's maybe not do it that way, because I think we're going to lose an answer that way. I like this x to the 4/3 is really like the cube root of x to the 4th. All right, so better option to solve this thing so we don't potentially lose answers. We would cube both sides. All right, and so we have x to the 4th equals 1. All right, and so if we do just take the 4th root, which is what that like divide by 4 power was, that 4/3. So we did 3rd power. If we then do the 4th root, that would be the 3/4 power. But by just doing that, we kind of forget that the answer to this is definitely x equals 1. But is there another number that you can do that number to the 4th power to get you 1? Like 1 times 1 times 1 times 1 is definitely 1. Is there anything else times itself 4 times that would give us positive 1? Well, yes, the answer is actually also negative 1. All right, so we have 3 critical values. So we're going to make a little sign chart here. And we're going to figure out what happens to our function. We know we have a 0 slope, and an undefined slope. All right, so we have a potential minimum or maximum at -1, a potential minimum or maximum at +1, and something weird is happening when x is equal to 0. All right, so let's plug in numbers in the middle. to figure out what's going on. A number smaller than -1, we want to plug into our slope, so like -2. Now, I'm going to go ahead and bring out the calculator for this one. Because I know this is going to be a decimal. Now, I'm not worried about the fact that this is a negative into what would be a radical, okay? Because this is a cube root. And we can do the cube roots and negatives. All right, so my answer here is negative. Plugging in a number between 0 and 1. Sorry, 0 and -1. We've got like -0.2. That's fine. And that's a +12. Putting a number between 0 and +1. Just need to get rid of that negative. Positive 0.2 is still positive. Then a number bigger than 1, like 2. Is negative. All right, so our graph is decreasing, levels out, increases, does something weird, gets kind of like vertical, all right, and then increases some more, and then decreases. So when it goes from decreasing to increasing at -1, so I know at -1 we have some kind of a minimum. I know we go from increasing to decreasing at +1, so this is some form of a maximum. All right, and here we go from increasing, we get vertical, but then we're still increasing. So this is kind of just one of those weird, it's like a saddle point, but it's not equal to 0. The graph just went like straight vertical for one moment of time, an instantaneous moment of time where it went straight vertical. All right, so that is not something that we need to worry about for our extreme values at least. All right, so decreasing. That interval would be from -infinity to -1, and then also from 1 to infinity. All right, we are increasing from -1. We get straight vertical for a second, and we're still increasing. So we don't have to kind of split it up at 0. We can just say from -1 to +1, we are increasing. Okay, an undefined slope would just be increasing still in this situation. All right, so we have an extreme value at -1 and +1. Okay, a minimum and a maximum. We're decreasing for a lot of time, but we're increasing just for this little bit. All right, let's see if we can take a look at this graph. Decimals just does such better of a job. 15x to the 1/3 minus 3x to the 5/3. All right, so something weird. Yeah. So at, that's not -1. Did I type this in right? 3. That's better. All right, got to trust yourself sometimes. All right, so we are decreasing until we get to the sets of -1. All right, and the matching y value would be -12. We didn't bother finding that. All right, but we knew this x value is where that minimum was going to be. We then increase. Notice right here, the graph is defined. It's fine. It just has an undefined slope for this precise moment in time, right here and right here only. This graph is pretty much straight vertical. Okay, that undefined slope that we were talking about. And then as it moves just a little bit to the right, yep, we increase, we reach this maximum, and then we decrease for the rest of time. Okay, so yes, I feel very confident about this. I'm pretty happy with what my results said and what my Desmos graph was showing me. All right, great. So hopefully we are good with increasing, decreasing, and things like that. Right, so cool. The next thing that we have are these things called critical points. Nope, not critical. Yeah, critical points. Did I already use critical points? What do we call these? What are these critical points? No, yeah, they were. All right, never mind. Still in the same thing. So given the graph of a function, this time we have the graph of the derivative. All right, determine its critical points. So that's when it equals 0 or undefined. So where does our derivative, this is the derivative, where does the derivative equal 0? Now, since this graph right here is the derivative of our function, not the function itself, I don't look for these spots where the derivative gives me a slope of 0, but where the derivative itself is 0. All right, so those 4 things would be our critical spots. All right, our sign chart would then look like this. All right, to the left of -2, where is our derivative function? Not is it increasing or decreasing, but what is the value of our derivative function? Well, the derivative function is down here. It's in the negatives. In between -2 and 1, our derivative function is in the positives. In between -1 and 0, our derivative function is in the positives. Between 0 and 1, our derivative function is in the negatives. Between 1 and forever, our derivative is in the positives. All right, so it's a little weird when you are given the graph of the derivative, not the graph of the original function, but this is the graph of a derivative. So it being negative, even though the function looks like it's increasing right here, this is the derivative. So the derivative's value is negative. So our function is actually our true function, not the derivative. The function is decreasing. Its derivative is negative in this zone. The derivative is positive in this zone. So that means our function is increasing in this zone. The derivative is 0 at these spots. So these spots might be the extremas. Okay. A true extrema only happens when we change directions. So -2, since we go from a negative, a decrease, to a positive, that means -2 would be a minimum. Going from decreasing to increasing, going from down to up means we had a minimum. To go from increasing to increasing means that at -1 we have like a saddle. So nothing we worry about. From -1, we were increasing, and then we decrease after 0. So we have a max. And then we go from decreasing to increasing, so that's another min. All right, so hopefully we can find those. So this would be, our decreasing from -infinity to -2, 0 to 1. And we are increasing from -2 to 0. And then also from 1 to infinity. All right, so again, I don't have to say, split this up into 2 pieces, because it is increasing. We flatten out for a second, and then it's increasing. Increasing can level out for a second and then continue. All right, it's still considered increasing. All right, so the next idea, okay, so we did this with given an equation, we found the derivative. So we can do it with the graph of the derivative. It's the same idea. The next idea, something just different, is talking about the second derivative. The second derivative is going to determine the concavity of a function over an interval. All right, so it's talking about how is the graph curving. Okay, so if you remember up here, we're talking about like the graph is increasing and increasing, but increasing in two very different ways. This graph is increasing, and it's increasing kind of in an upwards manner. All right, this is what we call concave up. All right, yes, the graph is increasing, but it's increasing in an upwards manner. So concave up. This graph is increasing, but it's not increasing in an upwards manner. All right, it's kind of increasing in a downward manner. All right, yeah, it's increasing, but it's increasing slower and slower over time. So this is what we call concave down. Now here our graph is decreasing, okay, but it's decreasing and continuing to decrease. So we would call this concave down. Here we're decreasing, but we're decreasing fast, and then it's kind of slowing down its decrease. So we would call this concave up as well. Okay, so these two are concave ups. These two are concave downs. Okay, so we want to be able to figure out how to find these intervals of concave up and concave down. And the way we do it is just by taking the second derivative and finding out when it's greater than 0 or less than 0 or equal. The spots where it's equal to 0 are called their inflection points or points of inflection, and that's just where our concavity changes. All right, if that's having or struggling to make sense, let's think about it this way. A linear function, y equals 3x plus 1, straight line. All right, it's increasing because f prime would just be 3. I guess I should say y prime is equal to 3. The derivative of y equals 3x plus 1 is just 3. Now 3, there's no variable here, is positive. It's always greater than 0. That means it is increasing always. But what's its second derivative? If you take the second derivative of this, y double prime would be, what's the derivative of 3? 0. All right, the second derivative is always 0. Now, concavity, the second derivative, being 0, means that there is no curvature to this line whatsoever. And that should make sense. This is a straight line function. There is no curvature to it. Okay? Hope that made sense. All right, so let's look at a cubic function. All right, the first derivative, 3x squared minus 12x plus 9, and that would go away, right? Great. If we set this equal to 0, that would tell us where we might have critical values, where our graph might have a maximum or a minimum. If we do the second derivative, 6x minus 12, if we set this equal to 0, so at x equals 2, this is what we call a point of inflection. Now, if we do a sign chart of this, if you plug in a number smaller than 2 and a number bigger than 2, smaller than 2 into our second derivative, so if I put 1 in here, 6 times 1 minus 12 would be a negative. If I put in a number bigger than 2, so we're 3, 3 times 6 is 18, minus 12 is 6, that's positive. So I would call this concave down because it's negative, and here I'd say concave up. All right, so let's take a look at the graph of this and try to put this together. Okay, actually, before I do that, here is kind of how you can think of these things. Concave up, let's graph it first. I'm lying to you. X cubed 6x squared 9x plus 30. Okay, so we have this graph. All right, so I changed my scale here, so we're looking at. We didn't really care about finding this spot. We didn't really care about finding that spot this time. Okay, we didn't really look at our first derivative. We looked at our second derivative. And our second derivative we looked at when x was equal to 2. No, it was -2, sorry. All right, so at -2, this spot right here, this is where our function changes concavity. All right, the left side of -2, our graph was concave down. I think I had that right. Did I type that in right? It was -6x squared. And +2. That was right there. All right, sorry. So +9. Oh my gosh. Well, that doesn't look nearly as nice. All right, I should have left it alone. All right, but still, at +2 is where our graph changes concavity. So you see how the graph is increasing. It even switches to decreasing for a minute. All right, here we're decreasing, but it switches to increasing. All right, and 2 is kind of like right in the middle of this graph in that mindset. All right, now the general idea is if you connect, all right, so we're saying that this part was concave down. It was increasing and decreasing, but this entire zone we consider concave down. The curvature, yeah, it's increasing. It even switches to decreasing. All right, but the curvature is in the negatives. Here, the curvature is in the positives. All right. Now, the best way to think about it, to kind of really gauge whether you have concave up or concave down, is to draw a secant line. Connect any 2 points that are in the same like interval. Okay, so we just have these 2 intervals here. So connect any 2 points in the concave down zone or any 2 points in the concave up zone. All right, and what you'll notice is that if you connect any 2 spots, so like this spot and this spot, for instance, if you connected those 2 with a line, that line would be underneath your function. Okay, even if you connect this spot to this spot, if you were able to connect those 2 with a straight line, technically the function would be higher than the line. Okay, the line is under the function concave down. Connect this spot to this spot even. If you connect those 2 things, the secant line would be above the function. That's why it's concave up. Connect this dot to this dot, for instance, and it's very clear to see that right here, this secant line would be above the function. Connect here to here, yeah, it's definitely above the function. But any 2 spots in the concave up zone, if you connect 2 dots on that zone, the secant line would be above the function. So that's one of the reasons why we call this concave up. Connect a spot over here to a spot over here, and you're going to have to cross over the function. Okay. Nope, that's not necessarily true. So we don't really talk about from the left to the right of our point of concavity. Okay. Point of inflection, I should say. All right, so I hope that made sense. Concave up, concave down. Okay, so let's put all of it together on an example. All right, so f of x equals this thing. Step 1, let's find any and all extrema. So step 1, we find our first derivative. Okay, we would set this equal to 0. Now to solve this thing, I think maybe we could factor -3 times 1 is -3. I can do +3 minus 1 to give me +2. So I've got -3x squared plus 3x minus 1x plus 1. I factor by grouping. So I pull out my -3 and an x, leaving x minus 1. These both have a -1, so I have an x minus 1. So my two factors, right. So my two spots where I might have an extrema would be x equals add 1 divided by -3, -1/3. Here, just add 1. So -1/3 and +1. All right, if I choose a number bigger than 1 and plug it into here, -3 plus 2 plus 1, sorry, bigger than 1, so 2. So plug in 2, that'd be 4 times -3 is -12. So it would be in the negatives. Plug in 0, that's going to be in the positives. Plug in something like -1, I'd have -3 minus 2. Yep, that's going to be in the negatives. All right, so -1/3, my slope was 0, but I go from decreasing to increasing, so this would be a minimum. I go from increasing to decreasing, so this would be a maximum. Great. So I'm increasing in the middle, I'm decreasing on the edges. Okay. So I've got my intervals of increasing and decreasing. My sign chart tells me that, and I've got my extrema. All right, part C, any inflection points. So I find the second derivative. So -3 times 2, -6x plus 2, and I set that equal to 0. I minus the 2. Divide by -6, and this time I get +1/3. All right, so 1/3 is my point of inflection. All right, if I plug in a number smaller than 1/3, like 0, I am positive, so I'm concave up. If I plug in a number bigger than 1/3, like 1, I am negative. -6 times 1 plus 2, so this is concave down. All right, let's check it and see how we did. -x cubed, x squared plus x. -1/3, 1, we have our minimum and our maximum. Great. Set at +1/3, we have our point of inflection. And again, connect any point from here to here. Your line would be under your function, concave down. Connect any point in between these two on this left side of the graph, all right? And our secant line would be above the function, concave up. Right? So that's the general idea here, what we're working with concave up, concave down. All right, here we have the graph of a derivative, right? So the points we care about would be here and here, all right? So our critical points are -0.5 and 1, all right? At -0.5, we go from decreasing our derivatives in the negatives to increasing, and then staying increasing, derivative goes back up. So -0.5 would be we go from decreasing to increasing. So from decreasing to increasing, so -0.5 is a minimum. We go from increasing our derivative is positive to increasing, so this would be like a saddle. All right, our second derivative, when does that equal 0? Well, that's when our second derivative here, the derivative of our derivative, is equal to 0. So we would care about these two spots. All right, so when x equals 0 and x equals 1. All right, and so for our concavity idea, our second derivative means the derivative of the first derivative. So our second derivative looks like it's increasing and 0 and then decreasing, and then we're increasing again. So concave up, concave down, and concave up. All right, so I hope that those ideas made sense. It's a little bit tough when you see the graph of the first derivative. You want to treat it like a function. But no, we look at for when it's equal to 0 for the critical. And you look at when its derivative, its slope is 0, all right, for those points of inflection. All right, I hope that that made sense. If something doesn't, please let me know. I know that's a long video, 40 minutes here, but a pretty big idea here in calculus.